All right, so the first inductive question we're going to look at is divisibility results. And they generally look like something like this. So prove that 3 to the power of 2n plus 4 minus 2 to the power of 2n is divisible by 5 for any positive integer n. So this is generally what they look like. There's some variation about it, but by just looking at it, it's not obvious that it's divisible by 5. But we're going to prove that. We're going to have a look how. So the first thing we're going to do, and a lot of this is very formal. So the first thing I'm going to write is proof by the principle of mathematical induction. Now, I've written it short form. You're going to write that fully. All right, if you didn't quite get that, it's principle of mathematical induction. I'm going to write it out again later on. So that's the first step. Like I said, some of this is going to be very formal. So firstly, the thing we want to do first is step number 1 is we want to prove it for P of 1. So if n equals 1, what we get is 3 to the power of 2 times by 1 plus 4. So it's a 4. Subtract 2 to the power of 2 to the power times 1. Okay, if we simplify that, we go, this is going to become 3 to the power of 2 times 1 is 2 plus 4. Take 2 to the power of 2. So this is going to equal 3 to the power of 6. Take away 2 to the power of 2 is 4. All right, chuck that in your calculator, you get 729 minus 4, which equals 725, which is divisible by 5. Therefore, P of 1 is true. Okay, so we wrote number 1 up here at the start because that's our first step. There's going to be 2 of them. First step is prove that it works for 1. All right, so now we're going to go to step 2, and what step 2 does is it says we're going to have a look at P of k and then P of k plus 1. So for step 2, if P of k is true, then 3 to the power of k, so what we're doing is we're changing these ones here, changing the n's into k. So 3 to the power of 2k plus 4, take away 2 to the power of 2k equals 5 lots of a. Okay, so if this is going to be divisible by 5, we're going to have to get 5 times something, where a belongs to the set of this weird z, okay, of the integers, positive integers z. Okay, so that's how we kind of set this up. So if P of k is true, then this. But the main maths comes from P of k plus 1. So now, so again, I'm being really formal here, but we need to be. So now, for P of k plus 1, what we do is we go back to our original and we put k plus 1 in there. All right, so I guess this question didn't really have it, but just on a side note, what we had originally was, it's assuming that we know that P of n, another way to write this is P of n equals 3 to the power of 2n plus 4, take away 2 to the power of 2n. And when I'm talking about P of k here, I'm just putting k in for my n's. When I was talking about P of 1, I was putting 1 in. So now when I have P of k plus 1, I'll put in my k plus 1 in there. So what I get is this thing equals 3 to the power of 2 lots of, change my n to k plus 1, take away 2 to the power of 2k plus 1. Okay, and we have to expand that. So, oops, I forgot my little plus 4 here. So good if you saw that. So if I expand this, I'm going to get 3 to the power of, multiply that 2 into the brackets, I get 2 times k is 2k. 2 times 1 is plus 2, plus 4 on the end. Take away 2 lots of 2 times k plus 2. Okay, again, I could probably simplify that a little bit. So 2 plus 4 is 6, so I could write that as 3 to the power of 2k plus 6. Take away 2 to the power of 2k plus 2. Okay, so I've just chucked it in and simplified as much as I can. The next thing I want to do is something that's a little bit tricky. And I could have probably left it in that first term, not simplified. What I want to do is I want to write out my answer, this first part, so it looks like this. Okay? Because if we rearrange this, if we take this 2 to the power of 2k to the other side, I'm left with 3 to the power of 2k plus 4 equals 5a plus 2 to the power of 2k. Okay, so I can take this part and make it look a lot simpler over here. And that's what I'm going to do. So the way I'm going to do that is I'm going to recognize that 3 to the power of 2k plus 4, and you've got an extra plus 2 in here. I could rewrite that as 3 to the power of 2 times 3 to the power of 2k plus 4. The reason I can do that is when we have the same base, the 3's, if we multiply them, we can add the powers. So if I added these powers, I'd get 2k plus 4, 2k plus 4, plus another 2. So I haven't actually changed it. I've just rearranged it a little bit. All right. So I'm going to just write the rest out. So take 2 to the power of 2k plus 2. And that's all I'm going to do for now. But what I notice is I can now see this was this thing here, which we rearranged and is equal to this. So I can substitute that in now, which is what I will do. So the next thing I'm going to do is substitute in, and I'm left with, so 3 squared is actually 9, so I can change that to a 9 and chuck in my, so times by 5a. So I'm just recognizing this thing here is the same as what we highlighted over there, 5a plus 2k to the power of 2k. Take, and I'm going to do the same thing I did before. I'm going to recognize that when we add a power, we could rewrite it as 2 to the power of 2 times by 2 to the power of 2k. And that'll be important later, the reason I've done that. All right, so I'm just going to move up here. I've cleaned up this side for us. So if I multiply that 9 in, I'm left with 45a plus 9 lots of 2 to the power of 2k. So a lot of people make the mistake of going 9 times as 2 to the base is 18. But you cannot multiply those because the exponent has to come first, and we can't do that yet. So put that at the front, so we get 9 lots of 2k. Subtract 2 to the power of 2 is 4. 4 lots of 2 to the power of 2k is 2 to the power of 2k. So use our dots to make sure we know we're multiplying in there. So if you have a look, what we get is 45a. Can't do much there. All right, but I've got plus 9 lots of this thing here. Take away 4 lots of the same thing. So if we treat these squares as x's, I've got 9 x's. Take away 4 x's. So I'm left with 9 minus 4 is 5 lots of that thing, that x. All right. So once you get to this stage, that's really good. What we can do now is we can realize there's a 5 because we were trying to see if it was divisible by 5. So the whole point of this is setting it up to get this 5 here. So I'm going to factor out the 5 from each. So if I factor out the 5 from the first one, so I should be able to do this if it's divisible by 5. 5 times 9 is 45, so I get 9a, because 5 times 5 is 45a, plus, if I take 5 out of that, I'm just left with 2 to the power of 2k. What I realize is I've got 5 times this whole thing, and all of these things in here are just numbers. So the formal way to write this out is where 9a plus 2 to the power of 2k is an integer, okay, which just means a whole number, as we already set the a belonging to the positive integers z. So we did that right at the start. Thus, 3 to the power of 2 lots of k plus 1 plus 4, take 2 to the power of 2k plus 1 is divisible by 5 if 3 to the power of 2k plus 4 take 2 to the power of 2k is divisible by 5. Okay, and that's the inductive step, realizing that if one of those dominoes falls, the next one has to fall. So just have to write one more statement out to finish it off, but again, it's quite formal. We'll just do it on the other side. So the formal part of the statement is since P1 is true and P of k plus 1 is true, wherever P of k is true, then what we get is Pn is true for all of our n's that exist in the positive integers. We've proved it, and then what we do is at the end we put in our special little brackets by the principle of mathematical induction. So you have to have this on there on the end to show how you've done this. But yeah, that's it. So a lot of formal stuff, but basically we're just doing that standard thing. We're proving the first one is true, and we're proving that the P of k plus 1 is true for all pk. Okay, so it's standard induction stuff, but yeah, this is the first example. So thank you.